Hello everyone and welcome. Today, we're going to tackle a super important topic from our Unit 11, the dual nature of radiation and matter. We're diving into the experimental study of the photoelectric effect. Now, don't you worry one bit. We'll go through it step by step, and I promise to make it so simple and clear that you'll feel absolutely confident and ready for your exam.
So let's get started. Look, we've all heard about Einstein's famous photoelectric equation, right? But was it just, a clever idea he wrote down on paper, or is that really how nature works? Today, let's be detectives. We're going to run the experiment, collect the clues, and see for ourselves if Einstein's radical idea about light was actually true.
And hey, before you start thinking this is just some abstract theory from a dusty old textbook, let me stop you. This is happening all around you. You know when you walk into a mall or a supermarket and the doors just swoosh open by themselves? That's not magic. That's the photoelectric effect at work in the sensor. So what we're studying today is real, practical physics that's powering so much of our modern world.
Okay, Chalo, let's step into our virtual lab and get our investigation set up. This is our crime scene, and it's here we're going to find all the clues we need.
So what does our setup look like? It's actually quite simple, nothing to be scared of. First, we have a sealed glass tube, a vacuum tube, which means we've sucked all the air out. Inside it, there are two metal plates. One is a special light-sensitive plate we call the cathode. When light hits this plate, poof, it shoots out electrons. The other plate is the collector plate, or the anode. Its only job is to catch those electrons. And of course, we need our meters. An ammeter to measure the flow of electrons, which is the current, and a voltmeter. See? Simple stuff. So here's the game plan. Our entire mission boils down to just two things. We're going to shine light on that metal plate, and we will change two properties of that light. First, its intensity, basically how bright or dim it is. And second, its frequency, which you can just think of as its color. That's it. We'll just tweak these two variables and watch very carefully to see what happens. This is how we'll get all our evidence. Right, on to our first test. The old classical wave theory of light, well, it had a very strong, very confident prediction about what should happen when you make the light brighter. Let's see if reality agrees.
And here, this is where things get really interesting. The old wave theory, which everyone believed for centuries, said that brighter light is like a bigger, more powerful wave, so it should hit the electrons harder and kick them out with more energy, making them go faster. Seems logical, no? But that's not what happened at all. The experiment showed that a brighter light kicked out more electrons for sure, but each one of those electrons had the exact same energy as before. They weren't any faster. This was the first big shock for physicists.
And this table makes it absolutely clear. Just look at the data. As we increase the light intensity from low to high, the photocurrent, which is just the number of electrons flowing, also increases. That part makes sense. But now look at that last column, the electron energy. We measure this with something called stopping potential. And what do you see? It's 0.5 volts, 0.5 volts, 0.5 volts. It doesn't change. So, our first clue is in. Let's write it down in our detective's notebook. Clue number 1. Increasing the brightness gives us a greater quantity of electrons, but it does not increase the quality, that is, the energy of each electron. For the classical wave theory, this result was a complete disaster. It just had no explanation for this. Okay, so if brightness doesn't decide the electron's energy, then what does? It's time to investigate our second suspect, the frequency of the light. In other words, its color. And, there's a fantastic story here about the scientist Robert Millikan. He was a brilliant experimentalist who actually thought Einstein's theory was total nonsense. He was so sure Einstein was wrong that he spent 10 whole years, doing these experiments with extreme care, hoping to prove it. And the amazing thing, his own data was so perfect, so clear, that in the end, he himself had to announce that Einstein had been right all along. That's how good science works. The evidence always wins. So now we come to the key question for this part of our investigation. What happens if we compare a bright red light with a dim violet light? Just remember, red has a low frequency and violet has a high frequency. What do you think the evidence will tell us now? And here it is, our second crucial clue. Just look at this data. When we use red light, low frequency, the electrons come out with a little bit of energy. Okay. We switch to green light, a higher frequency, and the energy goes up. And with violet light, the highest frequency, the electrons come flying out with the maximum energy. It's crystal clear. The energy of the electrons depends directly on the frequency of the light.
So we have our two main clues. Intensity controls the number of electrons, and frequency controls their energy. Now let's put this evidence together for the final reveal.
We're going to plot a graph now. And I'm not exaggerating when I say this is one of the most important graphs in all of modern physics, so pay close attention. On the vertical y-axis, we'll plot the maximum energy of the electrons. And on the horizontal x-axis, we'll plot the frequency of the light we're using.
Okay, let's take the data points we collected from our experiment, one for red, one for green, one for violet, and let's just place them on the graph. See? Can you see it? Even with just a few points, a definite pattern is already taking shape. It looks like they're all lining up. And when we connect them, just look at that. A perfect straight line. This is not a coincidence. This is the moment of truth. This beautiful, simple, straight line is the experimental proof of Einstein's photoelectric equation. It predicted that the relationship between electron energy and light frequency would be exactly linear, just like this.
But this graph gives us even more. Its slope, or its steepness, isn't just a random number. Millikan calculated it and found it was equal to Planck's constant h divided by the electron's charge e, two fundamental constants of our universe. And look where the line hits the x-axis. That point is the threshold frequency, the absolute minimum frequency of light you need to get any electrons out at all. And from the slope of this graph, the value of h was calculated. This number, it's a fundamental constant that defines the entire quantum world. And guess what? This value was a perfect match to the value of h found from completely different experiments. The evidence was just overwhelming. Our investigation is complete. Case closed. Einstein's revolutionary idea was not just a theory. It is an experimental fact of nature. All right, our detective work is done. Now let's put on our student hats and focus on what is most important for your exams. These are the points you absolutely must remember, and we'll also look at a common trap that many students fall into.
Please take a mental screenshot of this slide. These are the 4 golden rules. 1. More intensity means more photocurrent, simply more electrons. 2. And this is crucial, the energy of each electron does not depend on intensity. 3. If you want more energetic electrons, you must increase the light's frequency. And 4. If the frequency is too low, below the threshold frequency, no electrons will be emitted, no matter how bright the light is. Now this is the #1 mistake students make in the exam. Please listen carefully. The wrong idea is that brighter light means faster, more energetic electrons. That is the classical way of thinking, and it is wrong. The correct concept is this: brighter light means more electrons. It is the frequency, the color of the light, that decides how fast or energetic those electrons are. Remember this difference and you will save yourself a lot of marks.
So we've proven, beyond a doubt, that in this experiment, light behaves like a stream of particles we call photons. But this opens up a fascinating new question. If something we always thought was a wave, like light, can act like a particle, could it be possible that something we know is a particle, like an electron, can sometimes act like a wave? We'll explore that incredible idea next.